Hello world and welcome to this edition of Tech on Fire with Blaze. I'm Blaze Stewart, architect at Atmosera, and today we're going to be taking a look at the CAP Theorem as we launch a new series on data. Hi guys, today we're going to be talking about the CAP Theorem and why this is such an important concept in database designs. We're going to be doing a series in database technologies over the next several weeks, but I wanted to start with this because of the fundamental nature of this idea, and it'll help clear up a lot of ideas concerning why certain databases behave the way they do and why it's difficult to scale some databases but not others. We're going to camp out on this slide for a minute because this is really where everything about the CAP theorem kind of comes into focus. Now, oftentimes you'll see the CAP theorem presented as a triangle where you have three different ideas that are really kind of in tension with one another. And you see this often presented as a Venn diagram in some cases. I like this presentation better, but it really does illustrate kind of what we're getting at when we're talking about the CAP theorem. Now, the CAP theorem takes its name from the three various ideas that are kind of in tension with one another. And it's just the first letter of each of those words. And that is consistency, availability, and partition tolerance. So let's define what each one of these means, and then we'll talk about the implications they have on database design. So let's talk about consistency for a second. Consistency basically means that all clients see the same data when it is written. Now that's really defining what we call strong consistency. There are different paradigms within the concept of consistency that have different ways of getting the data within a session or within a region or whatever it might be. But for our purposes today, we're going to be assuming that consistency means strong consistency. That basically means as soon as I write anything to a database, any client that goes to read that data will read exactly what was written the last time that write happened to a particular row or column or a particular data set, whatever that might be. So partition tolerance is the next one, and that basically means that a system can continue to operate even in the event of a network failure. Now this is talking about network failure within the context of a database cluster. So if there is network failure and a given node can't talk to another node, what ends up happening in that case is the database node can act as a database in of itself. It can still receive queries, it can still receive write operations, and it will basically store those transactions. And once database connectivity is restored, it can then replicate that to other nodes on the system. So availability basically means that a system continues to function when a node on a cluster goes down. So imagine if you have a 3-node cluster and one of the nodes on that cluster goes down, the other two nodes can still receive all the writes and still receive all the read operations as if the database was still in a healthy state. And then when that third node that went down comes back online, all those transactions will be replicated back to that third node and it will be restored to a healthy state and then be able to rejoin the cluster and be able to handle some of that new work that's coming into the cluster. So let's talk about what these mean in relationship to one another. Sometimes these are presented as pick two. Now, what that means is basically you have these online and you have a database that prefers two of these at the expense of the other one. I don't think that this is entirely accurate because it's really not about having two of these in your database paradigm and completely ignoring the other one. It's more about trying to figure out what mix of each one of these you have in your formula. And you're typically going to have a database technology that's going to lean heavily towards two of these at the expense of the other one, but it doesn't always disregard the other one depending on what database technology you're talking about. So it's really not about picking two, it's more about preferring two. So if you want to think about it in those terms, it's not quite so black and white, it's more gray. So as we go through this, don't think that because a particular database technology is going to lean towards two of these that it's completely neglecting the other one at the other one's expense. So the first pair that I want to talk about is consistency and availability, because this is probably what most people are going to be familiar with. The CA databases are typically going to be our more traditional RDBMS databases. The reason why that CA databases are the more traditional databases is because partition tolerance in the old days of databases was not usually a problem because you had very reliable networks. Databases were deployed on local area networks rather than in the cloud. So the networking between any of the database nodes was usually local. So if something went down in the data center, usually it was systemic. Everything in the data center went down. So the database didn't really have to worry a whole lot about partition tolerance. Rather, it just needed to ensure that the database nodes were available and there was consistency available there as well. So whenever a write happened, it was replicated across all the database nodes and it was available to all of the clients that were trying to read that data. So that's why you see these more traditional databases, MySQL, Oracle, SQL Server, in the CA combination over here on the left. Next, let's talk about consistency and partition tolerance. Consistency and partition tolerance deals with networking issues. So there are databases that tolerate network outages and continue to function. The main trade-off in this particular paradigm is that you probably don't get all the data that is available in that database because one of the partitions might not be reachable across a given node. So you can still read data, but it's not going to be all the data that's available in that given database. Some examples of this would be document databases, typically like MongoDB or Redis. And for these kind of databases, it might not be important to be able to read all of the records in a given database for a given read. Many times these are just looking up single instances of records. Maybe it's just loading a single document or a single key value pair and is reading those values and writing to those without trying to query across large document sets and trying to get all that data out of these systems. Rather, it's just trying to read and write very transactionally without doing a lot of heavy queries and aggregations and those kinds of operations. For applications that use these kinds of databases, the database will still be available even though the requested record might not be available in this case, and it might be that you just get something back from the database saying unavailable at this time, but the database is still able to function even though the database node that contains a given piece of data is unavailable at that time. CP databases generally have high availability because they don't depend on the network to be available for the data to be available. So you can still have those partial reads even though a given node or even a given sector of a database isn't available. And this also allows for interesting sharding mechanisms where you can have partitions that are parts of a cluster. So you can shard data across a partition that is a cluster of nodes that is replicating across those partitions. And then you can have a cluster of clusters essentially that gives you a high performance database for reads and writes in this kind of setup. Let's talk about these last two now, availability and partition tolerance. Now, availability and partition tolerance are two that you typically find in big data workloads. You typically don't find these in application-oriented databases because application-oriented databases like to have consistency available. So what that means is that I write my data, and as soon as I write my data, whoever reads that data reads exactly what I just wrote in the order in which I wrote it. Now, availability and partition tolerance, though, kind of sacrifice that for scalability and for expediting reads across databases. So what these do is basically write data, and once the write happens, there's a replication process that happens to replicate data across all the nodes, and that can take some time to complete. But what that implies, though, is that there is a lag time between when data is written and when it is read. There is a potential that the data in a read might not be consistent with the latest write of that data. And so that's why it's inconsistent. The data will be eventually consistent after the replication process happens, but in that case, it's not guaranteed to be consistent like we see with MySQL databases and SQL Server or Mongo or Redis type databases. Some examples of this would be something like Cassandra or Couchbase. Now, the real boon of these kinds of databases is that they scale horizontally very well. And so you can query across terabytes of data that is spread across multiple partitions across a wide geographic area, and you can still get results back. So these are generally for read-heavy, query-heavy databases, typically what you would find in big data workloads. As I said a moment ago about picking two, it's really not about picking two as it is as much as preferring to. And it is possible in some database solutions to tune the consistency so you have stronger consistency or you have weaker consistency. And that has trade-offs on availability and partition tolerance. Or you could tune it more for availability and lose some stronger consistency, or tune it for more partition tolerance and lose some availability. Depending on what your needs are, you can kind of move the slider around and it will adjust one of the other sliders, if you will. So you can't have all three of them pegged at the same time. But if you move one then it's going to have implications on the other two. And so you have tunable consistency in something like Cosmos DB, or you might have the ability to geo-replicate data with something like SQL Server, but it becomes a read-only copy at that point, and there might be some availability issues that I can't do writes against that data. So there's trade-offs depending on what it is that you're trying to do whenever you're trying to design a database system. The bottom line in most modern database systems or most modern applications is generally that you don't have a single database to do everything for you. No one of these databases does everything well. So typically what you end up having is something that is going to be a combination of different database technologies. So here's a summary table of what we've just discussed concerning the paradigms with the CA, the CP, and the AP different databases. So as we discussed with CA databases, the strengths are that all the data is available once it's written for whatever the transaction might be. So you have strong consistency and it's already available the minute that it is written. The weakness is that this one doesn't tolerate network outages, which might not be a problem if you're just working on a highly reliable network like a local area network. As we said, examples are SQL Server and Oracle and MySQL. Some use cases that we haven't talked about given this one would be things like transactional applications. So this would be your typical e-commerce like applications or things that are doing a lot of IO against the database. So they're doing read operations and write operations in kind of a mixed mode. And you have mixed use databases such as that. So these are really optimized for application oriented databases. And one reason why they serve applications really well. CP databases, as we mentioned, these are good for operations that might be available for when a node partition fails. The weakness being is that some of the data might not be available if that happens. Some examples are Redis and Mongo. These are really good for write-heavy databases and caches. So in the instance of document databases like we see with Mongo, that's really conducive for data that's being written often. And it can also be read often. It's just more conducive to write-heavy databases where you're expecting to update records consistently and over again, rather than read data across multiple records and query that data, aggregate it, and do all those kinds of operations, which you might see in something more like an RDBMS or something like that. And then, of course, caches are one use for that as well, like you see with something like Redis, where you store data and you read from that data quite a bit, or you just might be working on a single entity rather than trying to query across multiple entities in that case. So that's one good use for a CP database. And lastly, the AP databases. These databases, as we said, they scale well horizontally. The data might be incomplete or might be behind the last operation for reads. But in any case, this is really conducive for read-heavy databases and big data workloads. So if you need a highly scalable solution that's going to scale well horizontally, that you can have high concurrency against that data, or you need to have a lot of data that is being aggregated together across multiple partitions for high performance or those kinds of workloads, this is where this kind of database really shines. And it's one of the main use cases for it, and really why you don't see it a lot in application-oriented workloads, but you definitely see it in big data workloads.
If you like this content, please consider visiting us online at www.wintellect.com, and there you can find about services that Wintellect offers, including training and consulting services. Also, please consider subscribing to this channel by clicking on the subscribe button and clicking the bell icon to get notifications when new content becomes available, and also comment down below. You can also follow me on Twitter at @TheOneMule, and also follow Wintellect on Twitter at WintellectNow or at Wintellect. We are constantly posting things about Azure-related technologies and things related to software development. You can also reach us by email at consulting@wintellect.com. Until next time, thank you.